Hello everyone, Mr. Walker here. This lesson is going to be on acids and bases. So in this lesson, what I'll do is I'll introduce you to acids and bases, the properties of acids and bases, what makes something an acid, what makes something a base, and then we'll get into the naming of acids and bases. Even though acids are molecular compounds, what we'll see is that it actually makes a little bit more sense, at least for the purposes of this course, to think of them as ionic compounds because we do name them starting off as ionic compounds. And bases, for the most part, they are ionic compounds, so we just name them strictly as ionic compounds that we've talked about before. So acids, if I can just jot down here, what we'll see is that it all has to do with hydrogen and the ion of hydrogen. And the ion of hydrogen that we're interested in is this one here, the positively charged ion. So for acids, there will be more of those positively charged hydrogen ions. For bases, there will be less of the positively charged hydrogen ions. So hydrogen is kind of unique. It can form covalent or molecular bonds. It can form hydrogen gas in this form here. Hydrogen only has one energy level, and for starters, because it is atomic number 1, there is one proton and there is one electron. So that means that its outer energy level is not full. So a couple of things can happen. It can either gain one more electron, and in that case it ends up having a negative charge, what we call hydride, or what it can do is it can lose its only electron, and then it has no electrons. So because it has no electrons, all it has is the proton. We simply refer to that as a proton. So from now on, when I do use the term proton, this is exactly what I am talking about, is the cation version of hydrogen. That hydrogen version that has lost its only electron. So yeah, it is just H+. And that is what acidity and basicity does have to do with, and also the so-called pH scale, which stands for the potential of hydrogen, that we'll take a look at visually on the next slide here as well. So really important for you to remember, it's an inverse relationship. More protons means a lower pH. As the number of protons, as the concentration of protons goes up in solution, the pH will go down. The more protons, the more acidic a solution is going to be. For bases, also referred to as alkaline, but we use the term basic most of the time. For basic solutions, it's the opposite. Instead of having more protons, they have fewer protons. And instead of having a lower pH, they have a higher pH. I'll also just kind of point out here that basic solutions, they have an increase in another kind of ion, which is hydroxide, OH negative. So when we talk about acids, they have more protons, fewer hydroxide. For bases, they will have more hydroxide and fewer protons. Let me just write that here as well. Bases, hydroxide goes up, protons go down. Acids, protons go up. The hydroxide is then going to go down. So yes, pH is on a scale. We show a scale visually, and it is a log or a logarithmic scale. And the basic range is from 1 to 14, but when you change from only one unit on the pH scale, what we'll see is that's actually a big difference. It's a 10 times difference or change in acidity or basicity. Hydrogen is essential for acids. You have to have hydrogen in order for it to be an acid. And what happens with that hydrogen, the hydrogen ion in particular, is it is released, or what we call donated, when you dissolve it in water. So we can have some compounds like this one here, HF, which is hydrogen fluoride. Here the hydrogen is acting as a metal, the fluorine acting as a nonmetal. Hydrogen fluoride. But when we dissolve this in water, it's going to release those protons. Protons are going to increase. So that means when it dissolves, I'll just put it here as H2O, then it does form an acid solution because of the protons that are increasing. You should realize as well, though, that not all compounds that contain hydrogen are acids. So if we take a look at one that we saw before, this molecular compound, a very common one that you should know, this is methane gas. It does have hydrogen, but when you dissolve it in water, which it can do, it simply does not form the protons. So in that case, you would end up with a neutral pH. It is not acidic and it's not basic either. So this is the pH scale that you probably have seen before. The standard scale, although as it shows here, can go outside of the range, but the standard scale does go from 1 to 14. But then we can see that, well, it can actually get into negative values, and those are the so-called superacids. It doesn't show it on this picture, but it actually continues to the right as well, above 14, and those are referred to as the super bases. But anything that we are going to encounter is going to be within the range of the 1 to 14. Right in the middle, pure water, pH of 7. Yes, you should know that. So that means that it is neutral. So if it is neutral, what that means is the number of protons or concentration, we use square brackets for concentration, but you can just think of it as the number as well. The concentration of protons that would make it acidic is exactly equal to the number of hydroxide, which would make it basic. So it's not acidic, it's not basic, it is neutral. As we go from the pH of 7 in this direction, what we have is more protons, more and more protons as we get further away from 7. If we go in the opposite direction, again, I'm going to focus on the protons here rather than the hydroxide. Oops, that shouldn't be more. It should be less of the protons that we then have. So what does it mean that it is a logarithmic scale? Well, if we take a look at some of the common acids that you will be familiar with, some of them you consume, like tomato juice and vinegar and maybe even coffee. So these ones here, placed where they are on this pH scale, they're probably not exactly pH 5, 4, and 3, by the way. But if we take a look at tomato juice, we can see that because it is a lower pH number, it is more acidic than coffee. It's only a difference of 1, but that difference of 1 is a 10 times difference in acidity. Tomato juice, citric acids like lemon juice, lime juice, they are 10 times more acidic than coffee. If we go from these juices to vinegar, vinegar is acetic acid. It's 10 times more acidic than tomato juice. So how many times more acidic is vinegar than coffee? Well, we go from 5 to 3. So that's actually 10 times 10, or 100 times more acidic. And of course, there are other things that you encounter as well that are kind of common. So battery acid has a very low pH. Gastric acid, this is in your stomach. Your stomach acid is actually this one here, hydrochloric acid, but there can be different concentrations and that results in the different pH values. As we go to more basic, you might recognize a bunch of these are kind of cleaning solutions. So those are fairly common bases that you would encounter in everyday life. You do need to know the properties of both acids and bases. So we'll start with the acids here. We'll do a lab where you'll take a look at a number of these different properties. So acids, in some ways, they're kind of like ionic compounds. In other ways, they're kind of like molecular compounds. Of course, the pH is less than 7. Before they dissolve in water, they could be solid, liquid, or gas, but once they do dissolve in water, they are soluble in water, which means they do dissolve. Reactions are going to take place. We're going to have the donation of protons. We're going to have ions that are forming, but because they do dissolve, we now give them the subscript AQ. So I mentioned that HF, hydrogen fluoride, you dissolve it in water, this will split up into the ions, but I'm just going to write it here as HF and now AQ. All that means is we took hydrogen fluoride gas, we dissolved it in water, and now it is an acid. So a couple things to look for. There has to be a proton. And in the formula, look for this as well, the AQ. These are a pretty good indication that the kind of molecule or compound that you're dealing with is going to be an acid. Because they form the ions, so this hydrogen fluoride, once you do dissolve it, it does form H+. It's a little bit more complicated than that. That's good for now. And this one here. So we do have the ions, so they will conduct electricity. Ionic compounds conduct electricity because there are charged ions that we do have in solution, and that's exactly what we have with the bases as well. You'll be using litmus paper. You may have used it before. It's a strip of paper and it's either red or blue. So if you have an acid and you dip in blue litmus paper, it turns red. If it is red litmus paper, it stays red. So kind of the key is to remember red. So whether it is blue or red litmus paper, if it's an acid, it should be the red coloration that we see. Some metals are quite active. Zinc is one of them. And if you do add zinc into a solution of HF, hydrofluoric acid, it does produce hydrogen gas. Hydrogen gas is given off in that reaction. Think about acids that you consume. Vinegar, acetic acid, is sour. Lemon juice, lime juice, grapefruit, orange juice, it's all sour. So if it is an acid that you taste, then typically they are sour. If you mix an acid with a base, they neutralize each other. So that stomach acid, which should be in your stomach, which is HCl, sometimes it goes up into your esophagus and it causes a burning sensation. So what do? Well, you take a base in the form of a tablet, an antacid, and it actually neutralizes that acid. So bases neutralize acids, acids neutralize bases. Acids that are formed between hydrogen and one other element, that's like this one here and this one up here, they're called binary acids. So again, the bi is talking about two. We only have two different elements. We're also going to come across some where they have a combination of the hydrogen that they always have to have, oxygen, and one other element or atom. So these ones here, they're called the oxyacids. And these you will find on the table of polyatomic ions or complex ions. So an example of that, and one that we will come across, is PO4 3-. This is a polyatomic or complex anion. This one here can combine with hydrogen and it will form one of these so-called oxyacids. So let's get into writing the names and the formulas for acids. I mentioned that they are molecular compounds, but at this point it's easier to think of them as ionic compounds because that is the first step in naming it as an acid, is to typically name it as an ionic compound first. So yes, name the compound as if it were ionic, where the hydrogen ion is the cation, of course, and everything else, whether it's one or more elements, is going to be the anion. Binary acids, that's what we already came across, where we only have two different kinds of atoms or elements. Binary. So for this one here, they will end in IDE. The anion, the non-metal, will have the ending IDE. We're going to change the name to call it an acid by taking the hydrogen in the name and putting in hydro. So instead of writing the entire name hydrogen, we convert it to hydro. So let me just write that up here. Hydrogen. So when we're naming these binary acids, we're just going to drop the GEN and we're going to use this hydro, and that's what goes in front. What goes in this little space here is going to be the name of the anion minus the IDE. So if it is chloride, get rid of the IDE. This here is what's going to go in that little space. So I call this, well, it's called either the root and sometimes I call it the stem as well. And then we're going to change the ending to ic and add in acid. We'll take a look at a number of examples, and this, by the way, is on the back of your data sheet. I'll go to that in a second, then we can take a look at it. But let's just take a look at the other couple of possibilities. The other two are for the oxyacids. So these are ones where it's still going to be hydrogen, of course. Hydrogen is going to be the positively charged proton, the cation, but now they're going to be polyatomic or complex anions. And of those polyatomic ones, some of them have the ending ATE, some of them have the ending ITE. If they have the ending ATE, we're going to take the name, get rid of the ATE, and change the ending to IC, and add in the word acid. What about that hydro that we stuck up here? We don't use that. There's no hydro if you have the ending for the ionic compound as ATE. Similar with the ITE ending, again, it will be polyatomic. Those ones that have the ending ITE, we're going to change the acid name to OUS, acid, and again, there's no hydro that we put in front. So let's just jump straight to a few examples here. In fact, a whole bunch of examples that we'll take a look at. Oh, these two here will be binary ones. So sulfur, phosphorus from the periodic table. When you have these ones, we do use either the full name, so we don't just use SULF and PHOSF. We use the entire name in most cases. In this one, we just drop off the US. Again, we'll see that with a couple of examples, but I have a couple here. So naming sulfuric acid, we use the full name sulfur. Just add in IC and acid. Phosphoric acid, everything except for the US. Add in the IC and acid. There are some other ones that are called organic or carboxylic acids. I have mentioned one of them anyway. Vinegar is acetic acid. That is an organic or a carboxylic acid. Organic means carbon containing. These are acids that have carbon associated with them. In your body, you have a whole bunch of different kinds of organic acids as well. You may have heard of lactic acid in your muscles, for example. There's pyruvic acid, so many acids in your body, and those are going to be the organic or carboxylic acids, except for the acid in your stomach, which is hydrochloric acid. So for these ones, what you're looking for is this ending. Usually the hydrogen is not in the front, it's at the end, and this is it right here at the end of this COOH. So kind of look for that. Sometimes it's drawn out a little bit differently like this. And this here is going to be a carboxylic acid. So it's this hydrogen and this one that are going to actually form the protons when they're dissolved in water. So I said I was going to jump to the your periodic table and the data sheet on the back first of all. So let's just take a look at that. So this is the back, and here you don't need to remember any of these rules that I just showed you, whether it's the IDE ending, the ATE, or the ITE. It actually gives you the rules right here. You don't need to memorize it, but of course you do need to know how to use this table, and that's what we're going to get a little bit of practice with. So it does have also the acid name, because we write the acid name first, and then we write the, we write the compound name or the ionic name, and then we write the acid name. These ones here at the end, the IUPAC system for naming, we actually usually don't use these. This is just the ionic name with the word aqueous in front. But that is not typically how we do name acids. Okay, so you have those rules there, and those are the rules that I just gave you as well. And the point is that you don't really need to memorize it. You just need to know how to use it. So let's take a look at a bunch of examples here, starting with, well, let's do one or two of the binary ones. With the binary ones, well, for all of them, you're going to have hydrogen, and the hydrogen is going to be in front for all of them, except for the carboxylic acid or the organic acids. So the hydrogen, and if it's binary, we're taking one of the nonmetals from the right-hand side of the staircase. So if we take this one here, Br, so this is our proton. This here, in the ion, it would be the Br minus. If it is dissolved in water, we write it as AQ for the state, and that's what you need to get into the habit of doing. So before we write the acid name and use those rules, first of all, name it as an ionic compound. At least in the initial stages when you're learning how to do this, that is beneficial. So I can't squeeze it in one row here, so I'm just going to write in all cases hydrogen up above. Just like for ionic compounds, the next one is bromine, but we change the ending to the IDE. This is hydrogen bromide, named as an ionic compound. But it's not just an ionic compound then, it is an acid because we have the AQ and because it does form the hydrogen ions when it is dissolved in that aqueous solution, dissolved in that water. So what am I going to do for the naming of this one? So the anion root or stem is going to be everything in the name of the anion except for the IDE. I'm just going to grab a different color here. So this here, the BORM, that's our root. I'm going to write that down again. Remember, all of these are lowercase letters. There are no caps in the naming. Because it has the ending IDE, I'm going to use that first rule. So what does the first rule say? I'm actually going to take the hydro from the hydrogen, and that's the first part of the name, hydro. Then I'm going to take the root or the stem, and that's what goes in here, brome. And the rule says change the ending to ic and add in the word acid. So this is a binary compound, a binary acid. It has the ending IDE, so if you take a look at your table for the naming, the rules, it tells you what to do. You need to have the hydro in front. You need to change the ending of the anion to IC, and you need to add in the word acid. Let's do another of the binary ones. These are the ones that are typically a little bit more straightforward. So I'll just do one more of these for the binary. So let's do this one, H, and let's have it with N. So the formula for this, we do still need to use the rules for the crisscrossing and make sure we have the right formula. So this in fact is not the correct formula. Why is it not the correct formula? Well, because hydrogen is 1 plus and nitrogen is 3 minus. Remember that this 1 associated with the charge on the hydrogen, it now goes to the lower right-hand side of nitrogen. We don't write it if it is a 1, but this 3 on the nitrogen goes to the lower right-hand side of the hydrogen. Put in AQ. So the correct formula is H3N. How would we name this if it were an ionic compound? Well, hydrogen again, we need to write first. And then this is nitrogen, but it is the ion, so it is nitride. Again, it's the IDE ending that we do have, so we're using the same rule and we're doing exactly the same thing as what I did in the first example. So hydro, we need to have that in first for the name because it has the IDE ending. NITR is going to be our root or stem, NITR. That's what I'm going to put in next, NITR. I'm going to add IC. I'm going to call it an acid, and this one here is our hydronitric acid. Of course, here I'm going from the formula to the name. You will have to go in the opposite direction as well. Why don't we leave that for the next rule that I'm going to do here. So here, this will be using one of the, this will be an oxyacid, which means it's using one of the polyatomic ions. Let's do this one here. So we have to have hydrogen, of course. Let me just grab my different color. And let's just jump to your periodic table. And let's just pick from there one of the polyatomic ions that we're going to use. Okay, so if you take a look at your table of polyatomic ions, let's pick one that has the ATE ending. Let's pick this one right here, which is nitrate, which is NO3 minus, if I can read that very small print, NO3 minus for the nitrate. So let's go back here and let's write that in. So we have H plus, we have NO3, 1 minus, one of each. They cancel each other out, so I don't need any subscript on the hydrogen. It's just NO3. You do need to make sure, of course, that you have the right formula for that. It is AQ. Naming it as an ionic compound, it is hydrogen nitrate. Okay, now it's a different ending. It's the ATE, it's not the IDE, which means it is a different rule that we do use. So what does the rule say? You don't put the hydro in front. That was only if the ending is IDE with the anion. We don't need to put hydro in front. What is our stem? Well, it's actually the same as the previous example, but it's a different acid, so it can have the same name. We don't put the hydro in front. We use the NITR, and we use the IC. So this is nitric acid. The one up above was hydronitric acid. This one is nitric acids, two completely different acids that we do have here. Let's do one going in the opposite direction. Let's write the name here first of all. This is a very common one. Phosphoric acid. So how do we treat this going in the opposite direction? There's no hydro in front, but we know it's an acid. We can put a box around here. What would be the root or the stem? That's what would go here. I won't write it down. We know that in terms of naming it, we would have to have the hydrogen in front if we're naming it as an ionic compound. Hydrogen. It's an acid. We know there has to be hydrogen. We can put our hydrogen in front over here for the formula. There's no hydro in front. It has the IC ending. So what this should tell us is that the ending has to be ATE. Remember, this one here was nitric. The ending was ATE. So you go to your table of polyatomic ions and you're looking for something where the anion has something to do with phosphorus. And what you'll find is that there's one that's called phosphate. Phosphate. Hydrogen phosphate. So we have our hydrogen, H1 plus. Phosphate from the table of polyatomic ions is PO4 3 minus. This is where you need to be really careful, right? So this 3 minus, that is on the phosphate. It goes to the lower right-hand side of the hydrogen. The 1 would just go to the outside of the brackets that we would write for the PO4, but we don't need the brackets here because that number that's coming from the hydrogen is just a 1. So it is PO4, and again it's AQ. That is our formula for phosphoric acid. Let's do two more here, just using the last of the rules, and that's where we have the ITE ending. So I won't keep flipping back and forth between the periodic table and this. So let's do one Let's do this one here, H2SO, and I just need to check myself to see which one we want to pick. It's going to be the SO3 that we're going to pick here, and that's AQ. Hydrogen for the name. So kind of think of it this way as well. We know that hydrogen is the cation. Everything else is what you're looking for on the table of polyatomic ions. So you are looking for something that has SO3. So there are a couple of them that do have the SO, but one is a sulfate and the other one is a sulfite. Don't mix it up. Make sure you're picking the right one. And this one is SO3 2-. If we work backwards, we know that it must be a 2- because this 2 on the hydrogen was on the sulfite. So it was actually SO3 2-. That is sulfite. Hydrogen sulfite. Now we just need to realize that it's the last rule that we're talking about. We have the ending ITE. We don't use hydro in the name, but we do need this here. Oh, and this is the one that's kind of weird. It's not just SULF. This is one where, again, just because it sounds better, we're actually going to use the full word sulfur. Because it's the ITE ending, unlike this one here, it's not IC when we name an acid, it's OUS. It's an OUS acid. And it is a sulfurous. So a little space in there, it should be all together, but sulfurous acid. Let's just do one more together here. Let's make this one chlorous acid. Actually, we'll have to do at least one more because I want to do an organic one. Chlorous acid. Okay, so now we have OUS, chlor. We know it has something to do with chlorine in here somewhere, but this is not a binary one. So this is not hydrochloric acid, this is chlorous acid, which means if it's OUS in the name, it must have ITE. So go to your table of polyatomic ions, take a look for something that has this and ITE, and that is what it is called, is chlorite. So this is chlorite, so it is hydrogen chlorite. Hydrogen chloride. I'm just going to go back to my purple pen here. Hydrogen chloride. So what do I do? H. H is always the 1+. Chlorite on your table of polyatomic ions is ClO2. ClO2, and it's a 1-. Okay, so there's no crisscrossing. It's just ClO2 with the AQ. That one is our chlorous acid. One more, just one more that I want to do with you guys. And that one that I'm going to do is just vinegar. So vinegar is acetic acid. Notice that there's no hydro in the name, acetic acid. So it's not using the first rule. So acetic acid, well, let me write down the formula here. So it is CH3 COOH. So that's what you're looking for. It will be AQ. COOH tells you that it is an acid. So the ionic name is hydrogen something. What is that something? It's everything except for that last hydrogen. Take a look at that. Well, it's more than one atom, so it's polyatomic. and it is called acetate. ATE ending means that it's going to follow the rule like the phosphate that we have up above, and that's why this one becomes acetic acid. Acetic acid for that one. So that's it for the acids. It won't take nearly quite as long for the bases. So first of all, with the properties of bases, these are the ones that instead of forming the protons, they're going to form OH minus, polyatomic anion, and that is hydroxide when you dissolve them in water. A lot of the properties, again, some of them are similar to ionic. Some of them are the same as the acids. So pH greater than 7 now, yes, they still dissolve in water. They conduct electricity because they form ions. There should be hydroxide. Ions, of course, are generated. Slippery to the touch, neutralize acids. I don't have taste here, but taste is quite often bitter as opposed to sour if you do taste them. For the litmus paper, blue is the key. So whether it is red litmus or blue litmus, if it's a base, it will be blue. Blue litmus stays blue. Red litmus is going to turn blue. It's easiest to think of these as having a metal. Typically, metals from group 1 or 2, so all of those, lithium, sodium, potassium in group 1, beryllium, magnesium, calcium in group 2, combining with OH, that's going to be a base. So let me just jot down a couple of these. I probably have some on the next slide. But NaOH, metal from group 1 with OH, that's a base. Ca, you still need to have the formula right here. OH2, calcium hydroxide, metal from group 2 with OH, that's a base. Other ones just with oxygen. So this one here, CaO, is also a base. Calcium from group 2. Magnesium, MgO, magnesium from group 2, that is also a base. So look for those, ones that have the OH and metals with the oxygen as well. That is most of them, and when we name them, they are just named as ionic compounds. So again, it's sodium hydroxide, calcium hydroxide, calcium oxide, magnesium oxide. They're just named as the ionic compounds. There are one or two exceptions, so I give you a table here that shows, yeah, a bunch of those same ones, and it also gives you some common name and common uses associated with them. This is kind of an interesting one here. So this is not the ammonium ion, this is ammonia, but when it does dissolve in water, what it actually does form is the ammonium ion, which means it's going to conduct electricity, and what it also forms is OH. So even though there's no OH in this formula, when you dissolve it in water, it does lead to an increase in OH, although not much, and that's why it is also a base. This is another fairly common one here. Sodium bicarbonate is baking soda, and that one is also a fairly common base that you'll come across.